Saxon Algebra 2, Lesson 117. It is interesting to me how you and I experience these lessons because for the most part, you watch them one at a time, but I record them in batches. So for me, I just finished 116 like 30 seconds ago, and now I'm launching into 117, but you could have a day or two pass between the times when you watch them. So, time travel, you guys, it's crazy. Lesson 1, lesson about notation. It's not about concepts. We're doing the same kind of problems that we've done in the past. We're just using what is called set builder notation. It's just the way we're going to use symbols. The ideas and concepts and calculations are exactly the same. We're just going to use a different set of symbols to do that. When we have talked about integers in the past, remember that's like minus, it's numbers like this, right? Where it's the whole numbers, but it's negatives and positives and zero, and then infinitely in either direction. It's not all the fractions and decimals, right? And when we've wanted to indicate a domain of integers, we've written it like this, haven't we? Sometimes I'll just stop there if I'm running out of room, but John always writes it out. So this is where we know we're supposed to take the domain from the set of integers, right? But now we're going to use a different way of saying this. We're going to say x because x is the domain, and this symbol means integers. So this says domain equals integers. This says x is an element of the integers. Okay? These two things mean the very same thing. It's just a different notation. All right? So we're going to express the different sets of numbers, the way we've talked about them, using these kooky letters, and then you'll see we'll use a different format when we actually write the problem out. So let me show you what all of these are. This means the natural or the counting numbers. We don't use these very often, but remember that diagram I've drawn with the boxes and the boxes and the boxes. This is where you started out, right, with your mom counting your little baby piggy toes after the bath. Natural or counting numbers. Then we moved into the whole numbers. We symbolize that with a W. Then we get into the integers. I already told you that's a Z, which is kind of weird, but it's fun to draw. Okay, so these are all the symbols we can put into an expression like this if we want to. Rational numbers. It's a Q with a little bar on the side. These are the rationals. We don't usually use those either. And then P equals the irrationals, the ones with the non-repeating infinite decimals, right? And here's the one that we use a lot in our problems, the reals, right? And then the biggest set of all, again, this is not a symbol we're going to use real often, is a C. This is the complex. It's kind of a fun little exercise in calligraphy to make these letters. Here's what they mean. This information is also provided with a lot of other details on page 476. Okay, puffy cloud of knowledge here. All right, so what we're going to do is we're going to use this notation when we write out our domains, and integers and reals will still be the two that we use the most. The reals is super easy to remember because it's an R, and the Z is totally random, but you'll just learn, oh, that's integers, all right? So let's look at how we might use this notation in a for real problem. And only have one example in this lesson, which A, shows you how straightforward it is, and B, kind of makes up for the fact that in the last lesson we had like 87 examples. So that's cool. So we are supposed to graph this, and this is what we get. I ran out of room, so I'm double spacing. Okay, that looks different, doesn't it? Pretend that that just goes on in one straight line. That looks different than what we've ever seen before. Let me read to you what this actually says. We're supposed, and it says graph on the outside. Sorry, I didn't write that. Okay, the problem says that. It says we're supposed to graph the set whose members are ordered pairs, x and y, where x and y are elements of the real numbers, such that y is greater than x plus 2 and y is less than minus x. Now what this means, okay, the reason this is squared is because we have two variables. So this is telling us that both the domain and the range need to be real numbers. And then these are the two conditions we need to satisfy. The way we have seen this problem before would be written like this. Okay, I'm just going to draw these lines so you can see the difference between them. This problem and this problem are exactly the same. Here are those. Domain equals the reals. That's that information, okay? So, it's the very same thing as this. We're just going to get used to seeing it in a different way, and we're going to get used to solving it in a different way. So, I'm going to, I just happen to have this handy piece of paper nearby. We're just going to cover that up. We're not going to lean on that, okay? We know that it's not just a number line. We know that it's a Cartesian coordinate system or a graph because there's an x and a y, and we can't put that just on a single number line. Real numbers, okay, that's cool because we always use real numbers on here. It's super hard to use integers. And so we want to graph these two things. So they're lines, we can see that. We see their inequalities. This one's going to have a dashed line, this one's going to have a solid line. So let's go ahead and graph this one. It's in the proper format, y equals m. So we go to the y-intercept, that's positive 2. And then we can see the slope here is 1 over 1, so then we go up 1 and over 1. There's our second point. And this is the one where we want to have the dashy line because it is not equal to, it's only greater than. Okay, and I am not going to test it yet. I'm going to draw both lines and then we'll test. Now here's the other one. This one has a y-intercept of 0, right, because it's plus 0. And the slope is negative 1, so it goes down 1 and over 1. That would be right there. And then this line, oh, I'm sorry. I wrote it wrong. It shouldn't have the equal sign there. Okay? And it looks like it still does. Now this, okay, this goes through here. This illustrates a really good point that I wanted to talk to you guys about anyway. When we choose a test point, because that's the next step in this, when we use a test point, I like to use the origin, not for any other reason except it's got 2 zeros in it, and that makes it super easy, right? The origin is the special name for this point right here, okay? when we're testing for the region, we can choose any point that we like. This makes a nice test point just because it's easy. But in a problem like this, where one of our lines or our shapes goes through the origin, then it's too confusing. We don't want to use that. That's just too hard. We can choose a test point anywhere. We just have to think about what it means. What I want to do is I want to choose the same test point and use it for both lines. I want to choose one that has easy numbers in it, and I want to be clear about why I choose the points that I choose. Sorry, I went and just got another color marker. I'm going to choose the point 1, 1 for my test point. The reason I chose that is because, number one, it's easy numbers. I like them when they're the same because I don't want to get confused about where I put the X and where I put the Y. If it's the same number, then I can't mess that up. So it helps me prevent mistakes. I choose the smaller numbers because the calculation's easier. And I want to choose a point that is clearly on one side of the line or the other for both lines. I want to be clear about that. Okay, so now what I want to do is I'm going to plug it into both of my lines and see if it's true. So first I'm going to test the line y is greater than x plus 2. Okay, so I'm going to put the 1 in for both of those. 1 is greater than 1 plus 2. 1 is greater than 3. Okay, it's fine that it comes out to be false. What it tells me is for this line, which is which one? It's this one, right? Let's do this. Let's call this one A, and this one B. This is A, and this is B. I tested here line A, and I found out that for A it's false. So now I go back and I look at my line. It's false, so that tells me the solution doesn't go this way, because this point tested false. So that means my solution must be on this side of this line. It goes away from that failed test point, right? Okay, so now I'm going to test line B. The equation here is y is less than minus x. Whoops. I substituted it in my brain. Okay, that's the equation for line B. Now I'm going to put in my test point. 1 is less than minus 1. I'm going to check and see if that's true or false. That's false. So again, it's fine that it failed. That doesn't bother me. Information. What it tells me is that for line B, this point also is not one of the solutions. So that means the solutions must be on the other side of line B. So I draw them this way, and now I can see the intersection where I have both A and B solutions. Sorry, I want to get another color. This is when my light yellow markers come into play. That means that this is the solution for this system of inequalities. They are linear inequalities, but they are inequalities. Does that make sense? Now, let me point out something interesting about this. This looks really weird, but we knew how to graph this because this solution is exactly like we've been doing for problems like this. The only thing that's different is that we had to decipher a different kind of notation in order to figure out what this problem was asking us mentally, and in this case, literally, translate it into something different. But in the future, our goal is to train your brain to look at this and go, oh, right, I get it, no problem. In the practice problem, I want you to notice the problem that you'll be doing. Graph, x is an element of the integers such that x plus 3 is greater than 5. This does not have an x and a y, this just has an x. That means the answer will just be on a number line, okay? And we'll have to do a little algebra to clean that up, won't we? But this just means graph this, clean it up and graph that, and show a solution where the domain is equal to the integers, all right? Translation, but no new calculation. All right, that's lesson 117. Thank you. Farewell.